Okay, I'd like to welcome everybody to this first Friday evening talk of the season. We have guests from the BAA solar section tonight, including Lynn Smith, their director, and this is a talk about the sun, solar energetic particles. Dr. Timo Laitinen from Central Lancashire University. Timo, I see that you're on the call.
Yeah, I'm here.
I'm going to hand the floor over to you, and we'll do any other notices about the next meetings at the end when we're taking questions. Timo, the floor is yours.
Okay, thank you. Can I check? You can hear me okay?
Yeah.
That's good. That's good. And the next step is to actually share the screen. That one. Okay, can you see my screen? Yep, I can see nodding heads in there. That's good.
Yes, we can see.
So a little bit annoying that the well, hopefully it's not masking anything. Yes, hello. Thank you for the invitation to give this talk to you. I'm going to talk about solar eruptions and space weather, and then going a little bit into energy particles, and trying to do a little bit on the radio as well as you know, kind of specialist on radio. So hopefully not showing that I'm not an expert on radio, but seeing what radio is being used in the solar physics science. You may notice that can you see my mouse move, by the way? Yeah, good, because I'm going to use it quite a lot. We are now University of Lancashire, so I haven't moved. Our university changed its name a bit over a month ago. So that's where we are now. To introduce myself, I'm a researcher at the University of Lancashire, and I'm studying solar-energetic particles, which is why I brought that into the topics, but also space weather and the heliophysics in general. I also do some teaching. I teach in our distance learning program on our solar modules, the first year Sun, Earth and Climate that has just started, and solar astrophysics. And just to give an advert about our program, where we have individual certificate courses on astronomy, cosmology, astrobiology, and okay, the Sun, Earth and Climate is not here, but it is one of our courses. And then you can study all the way to BSc astronomy. So if you're interested in, you can use the QR code or the links down there, or go to our institute webpage as well. And if you have any questions about that, I can answer as well. But after this advertisement, we can get into the business. So the outline of the talk, I'm going to start by talking about observations, observing sun's activity, and then about the solar eruptions, how they are observed, what we have learned from them, how they reveal their many phases. Then talk a bit about the sun's effect to Earth and humanity, about the space weather, then a little bit on solar energy particles and the future missions. Well, actually, I should have written new missions, which are not so new anymore because time kind of flies. So to start with, we think about the sun, we see something like a yellow dot somewhere in the horizon or in the middle of the sky. And if the sun is setting in a nice environment, we can carefully a little bit more. Of course, at this point, I have to say that do not stare at the sun, do not use telescopes if you don't know what you are doing. I'm sure you all know what you are doing, but it's good to bear that in mind. If we have some nice telescopes that we can use good filters or project the sun into a screen, we can see something like this. So here's the sun as seen today a couple of hours ago. You can see the disk in this monochrome image. You can see some sunspots, which are very prominent at this time of the sun's life. And you can also see a little bit of lighter areas in there, in a couple of places, often close to the sunspot. Then we can limit the light of the sun. We can start looking at the sun at certain wavelengths, most famously H alpha, which looks at the particular temperatures on the chromosphere. You can see the sunspots. The sunspots aren't always visible in the solar disk. In H alpha, for instance, these sunspots and these sunspots don't seem to be visible. Some sunspots are big enough that they can be seen there as well. And you can see lighter areas, which are very often linked to the sunspots, and show kind of a little bit more activity on those regions. And then we have the prominences, these dark lines, dark ragged lines, going from here to there in the solar surface. Some of these can be very long, like this prominence in here. And then some of the prominences we see over the limb of the sun as protuberances. It's the same thing, it just looks a little bit different. Then if we are lucky, or if we plan our life very carefully, we can end up in places where we can see solar eclipses, where the sun goes behind them. Well, the moon goes in front of the sun, and then we can see the atmosphere of the sun. So we can see the bright glow of the corona of the sun and all the structures that we have there. Of course, this is only image of one time of the sun. This isn't from today, the sun solar eclipse, but these two are. And we can look at the sun at a longer range of times. So this is the sun imaged over the last 15 years. And you can see that the number of sunspots changes from time to time. So 15 years ago, there were some sunspots. It's kind of difficult to see because sunspots come and go, but you can see that the sunspots appear in more quantities at some times, and then there are some very quiet times. The 18 and 19 seem to be very quiet, and then they start to be coming up again. And this is from I've picked the most sunspotty days in a 3-month period around this time of year, just to demonstrate that the amount of sunspots varies. This has been done for quite some time. In fact, a very long time in terms of astronomy observations. Ever since Galilei invented the telescope and observed the sun, and saw that there were some sunspots in there. So the sun wasn't a perfect sphere. There were some blemishes in there, which I think got him into a little bit of trouble. But ever since that, the sunspots have been observed. Maybe
your Zoom, but you're falling asleep.
Maybe a little bit less irregularly in the beginning. And really regularly from 1750s onwards. So we have a very long stretch of observations. This must be one of the longest observational time series, continuous time series that we have. And we can see that there is this sort of decadal variation of the intensity, and that of course is the famous 11-year activity cycle. So every 11 years, give or take a little bit, it's not exactly 11 years, we have sunspot maximum, and then it dies down into a low level of sunspot and so forth. We see some other variation here. We have kind of a quasi-centennial cycle, Gleisberg cycle. Then we have, of course, the very famous Maunbury minimum, where for 100 years we didn't have any sunspots. So clearly there's something going on in the sun except just having the plain old sun doing nothing. We can observe this with spectral lines as well. We can look at the H alpha line, and we can see that in the beginning of the solar cycle, the prominences are kind of fairly well regimented at these high latitude belts, and then things get a little bit more chaotic, and then at the end we get into a very quiet time. This actually was a very quiet time even for the sun's quiet time views. In calcium line, you can see the Planche regions, these lighter regions, increasing and going towards the lower latitudes. as the activity cycle progresses, and then we get into the quiet time. There's only so much we can do from the ground because we have the atmosphere. We can't see X-rays, we can't see ultraviolet. There's a lot of radio that we can't see. So for that reason, it's nice to go to the space where we can actually do these observations. And this image is kind of a collage of observations of Solar Dynamics Observatory, which was launched 15 years ago. It still feels like a new instrument, but yes, it's 15 years ago. And the idea there is that it's a telescope that has a lot of filters that let various bands of ultraviolet light pass through. And these bands have been selected so that we get interesting spectral lines, because the spectral lines at certain parts of element and spectra are tied to the conditions where the optimal conditions that give birth to the radiation at those wavelengths. So if we start from the top left, we are looking at actually continuum image where we have a 5000 Kelvin image. The solar surface is around 600 Kelvin. And then we can look at various lines. I think this might be calcium line, but I don't actually know which lines these are. So when we go up from the photosphere, the solar atmosphere cools a little in the chromosphere, and then it shoots up in a short range called the transition region up to millions of degrees in just a few hundred kilometers. So it's really a very, very big change from here to here. We also see that at these higher temperatures, the sun looks like a little bit of a furry ball, which means that the hot gas is around the sun rather than at the surface of the sun. You can see that the surface here is the darkest bits are really dark, so the solar surface does not radiate at these temperatures. It's really in the corona rather than in the atmosphere, which is called corona, rather than on the surface. Then we see some bright areas. There's a big bright area coming in here, and you can see that there's clearly some activity going on. There seem to be some kind of looping structures, and if we look at the continuum image, we should be seeing in just a moment there's an area with sunspots exactly at the same location. It's the same in here. This area is linked to this area, so the sunspots, which are magnetic phenomena, are clearly linked into these highly energetic emission regions in the solar atmosphere. We can take these extreme ultraviolet observations. This is from the SOHO spacecraft, just because with SOHO we can go to year 1996 when it was launched. My scientific career actually started in there, so I'm kind of tracing SOHO as I'm going. SOHO was launched at the quiet period of the sun. It was actually supposed to be running only for a couple of years, so it was a solar minimum mission. But then there was a maximum, then there was a minimum, and there was a maximum again and a minimum, and now we're in maximum, and it's still going almost 30 years later. You can see that in ultraviolet, extreme ultraviolet, the solar radiation changes really drastically. We go from very, very dull, uneventful sun with a couple of bright points into these glowing areas that are really dominating the solar atmosphere. Then back to the minimum. This minimum was a very long minimum. It was a year longer than we thought it would be. And then it increases again to something not quite as big as the previous. And getting to the next minimum. And these 5 last years, I made them myself, and I'm not an expert in making these images, so don't take the brightness comparison between these and these two seriously. But we can see that there is the same 11-year activity cycle also in the corona, and it's actually much more prominent than if we just look at the solar surface with the continuum light and see the sunspots. Then we can go and look at the sun at a little bit shorter time scales, so hopping from years to days. This video shows the solar continuum image on the bottom. You can see a sunspot in here. You can sort of see the sunspot in here, and then overlaid with some transparency tricks, the extreme ultraviolet, and you can see these loops going from here to there. And these loops, if you look at these loops, compare them to the sunspot picture, you can see that these loops are kind of going from sunspot area to another. So these loops are kind of connecting these areas. These loops are connecting this to here, and there seems to be some kind of looping between these that might be going over there. These loops are magnetic flux tubes, and they are connecting the magnetic field that bursts through the solar surface at these sunspot locations. And they are bright because they are filled with plasma, and the plasma is constrained to moving along these field lines. So these are really tracers of hot plasma and the connection between the magnetic ones. So let's put the video on motion. And you can see that there's quite a lot of dynamics in very short time scales. There's also a lot of dynamics in the sunspots. So they are in continuous motion. They're not in continuous motion all the time. They can be very stable for long times, but this area really is a very active area. And you can see that there are some brightenings here in the EUV loops, and you can see that there are some eruption kind of things as well. So something is going on, and some very strong brightenings, flares are taking place. So now I've used the F word, which in this case is the flare word, and the flare word is related to the magnetic activity of the sun, and it can be going on all the time at various different scales. So not just in the big flares that we are talking about with large eruptions, but also on smaller scales. Okay, so let's look at the history a little bit. This is a drawing by Richard Carrington in 1859. And Carrington was a solar observer. He observed the sunspots, he drew sunspots. That's how we had the sunspot records. People were regularly looking at sunspots whenever there's no clouds, of course, and counting sunspots and also drawing sunspots. So there's a big archive of sunspot drawings around for people to investigate. And one day when Carrington was looking at the sun, drawing the sun, he noticed something that no one had ever reported before. He noticed two very bright areas partly overlaying the sunspots, sort of kidney-shaped areas. Furthermore, these areas weren't just still. They were moving in about 5 minutes from here to here and here to here until they disappeared. So something that no one had ever reported before. So this was very interesting. There was another scientist, Hodgson, I think, who also reported it. So it wasn't just his figment of his imagination. It clearly was something that was real and was worth reporting. What brought this into more prominence was something that happened 18 hours later, because there was a worldwide display of aurora. Aurora, of course, were very well known, not understood in the least. No one knew what they were about. But 18 hours after this flare phenomena that Carrington saw, the aurora was seen in Panama, in Rome. There are reports that in southern states of the US, you could read newspaper in the light of the corona in the middle of the night. So it was really, really impressive aurora. There were also some other observations. Magnetographs were drawn in Kew in UK, and during this flare that Carrington observed, of course, he didn't know it at the time, there was a little blip in the magnetic field. So a little bit of a blip changing in the magnetic field. And that was would have been curious on its own with the timing. But the timing with the aurora was much more significant. It was a huge increase in magnetic field, huge deviations in magnetic field. And it had really big practical implications because they were living in information age. The telegraph wires were spanning across continents, and with these magnetic field changes, of course, induce electric fields into conductors and drive currents. So these currents that usually would be flowing in telegraphs were hugely increased, and the sparks would be flying through the keys when they were not open. The operators would get jolts, and they would also cause fires because the telegraph messages were recorded on paper, and this paper wasn't exactly fireproof. So there were real consequences of this early geomagnetic storm. I just have to say that Carrington was really, really lucky because this was the biggest storm that we have seen since Carrington's observations. And Carrington had 5-minute window. If he had started his observations 5 minutes later, he would have missed it. So with this luck, he still had the wherewithal of being a good scientist and carefully saying that these things might be linked. And as it turns out, they were linked, but at that time, there was no way of explaining what that linkage could be. Okay, so nowadays we of course have much more ways of seeing what different phenomena we have with these eruptions. We have the EUV images that I showed you earlier. We can measure X-rays. So as a kind of go-to thing, the NOAA's, the Americans' GOES satellite measures the all-sun X-rays in soft X-rays. We have this classification from A to X. All of these, each of these level are factor 10 apart. So if we go from here, 10, 100, 1,000, 10,000 times larger intensity than we are here. And this was an X-class flare, so a very big flare. And you can see that there's a strong energy release. There's a lot of radiation actually saturating the imager. And then you can see that it sort of slowly dies away. There are a couple of other flarings as well. We can see, of course, on optical wavelengths. Here at Earth, it's a different flare observed by the solar telescope, the biggest. And here you can see the flare ribbons that would in here be in optical. Somewhere here on the foot points of the loops, we can see the arcades, which here are dark because they are so hot that they don't radiate at the temperatures of H alpha that this image is taken from. And we also have image flares with X-rays, both soft X-rays and hard X-rays. This is from Yoko satellite, and we kind of have a good picture of what's happening. So what's happening is there's an energy release up here, and that's where everything starts. So did I have? Yes. So the idea is that the loops that we are seeing and the brightening at the foot points is actually kind of an afterglow effect. It's not the thing. The thing takes place above these flares, where the magnetic field, magnetic loops that are going from the solar surface up in here and down in here, they get so close, pushed so close to each other that they can reconnect. And reconnection releases a lot of energy, and that energy is given into both the plasma and particularly particles. So the particles are accelerated. They are following these magnetic field lines to the foot points, and they cause the heating of the foot points, and then that heating will result in filling of these loops with material that then radiates in soft X-rays and EU. We also can get the hard X-rays and gamma rays, both in here in the loop top, and hard X-rays on the top and gamma rays in the bottom, where these protons hit the solar atoms so hard that they start to have nuclear reactions. So this is kind of the current view of how these solar flares work. We have radio observations, as you might be interested in, and typically when we are looking at radio observations, we have these kinds of radio spectrograms. We have the time in the horizontal axis in minutes, and then we have the frequency, and we get these bursts of different kinds. So we get these very wide band bursts spanning decades in frequency almost simultaneously, and then we can have these sort of gradual drift types of bursts that start from higher frequencies, and it can take up to several tens of minutes, up to hours, to drift into lower frequencies. And the solar physicists have really gone all the way to figure out good names for these bursts. There are type 1, type 2, type 3, type 4, and type 5. Type 1 actually is more of a magnetospheric phenomenon. These others are then reflecting something happening in the sun. And we have quite a good idea of the physics of this, because we know that in many cases, these radio bursts are caused by plasma vibration. If you prod plasma, it will start vibrating at a frequency that depends only on its on the plasma's electron density. And those vibrations are then generated into radio waves. So if we see radio emission at a certain frequency, we can essentially say what are the conditions in there. So if we know the frequency, we know the density, and if we somehow know how the density varies from the solar surface out into the interplanetary space, so from here to I think it's 20 solar radii, which is about 10% of AU. We have some kind of models and in part observations, but mainly models that say how the density varies at different regions. So then we can trace which distance from the sun this radiation is. Now, this is from a very early paper of mine, and I did not do this analysis. We had radio expert. I was doing the particle side. But you can see that this radio burst starts from about 1.6 gigahertz. It goes down. These different panels are from different Earth-based observatories, all the way down to 0.5 megahertz. And this bit is done with wind spacecraft. So these are space observations. And you can maybe see that this is not completely simultaneous at all frequencies. There seems to be a drift. And from that drift, we can deduce that this burst is actually caused by very fast relativistic electrons, almost relativistic electrons that are accelerated somewhere in the process, in the eruption processes, and then escape all the way to the observing spacecraft. And this is the radio that is emitted at the given location where the particles are. Sometimes the particles won't get very far. They are possibly stopped because the magnetic field is not open. If you look very carefully, probably not in these images, you can see U bursts where the particles are going up and then back down, and the radio frequency drifts show the same. So there's another place in here where we can see particles escaping into interplanetary space. We have also we have also type 4, which is kind of diffuse cloud of material, possibly in some coronal structure that accelerates particles, and type 2, which is then related to the shock waves that are related to the eruption of the particles. We can also do radio imaging, showing here two kind of an extreme ends. There's the low frequency radio. I don't actually know the frequency ranges. Oh no, sorry, I do, because they are in this picture. So it's a radio telescope spanning from Ireland to Poland, and it has been quite good at observing the sun. Of course, it does observe astrophysics as well. But here is a picture from Hamish Reed's paper, where the radiation is observed at low frequency, 75 hertz to high frequency, 75 hertz to 40 hertz, and you can see this kind of pattern, this kind of pathway where the particles have been following. The particles are charged particles, so they follow magnetic field lines. So the authors of the study actually could trace where the particles would be going, what kind of structure, what kind of the particles would be confined in. Then you can go to higher frequencies. Here's the Nobeam radio telescope at 17 gigahertz, 45 meter telescope, as far as I remember. And then you can do observations of the radio in the flaring region as well. Okay, so we've gone to radio. I mentioned that there are some stuff coming out from the radio, from these eruptions, and we know that something happened 18 hours after the Carrington flare. And what that was, the researchers had no idea until 100 years later, when the Americans launched Skylab space station, where they had a solar observatory, where they had a coronagraph. Now, a coronagraph is a device that pretends to have solar eclipse all the time. So there's a little disk that is in the somewhere in the focal plane, somewhere in, I'm not an expert on optics, that blocks the sun out. And when the sun is blocked out, then you can see what the corona is doing. And what they observed, for a very big surprise, was this kind of a cloud that was moving. It was moving, took it half an hour for it to move from here to outside of the view. And they calculated that that would be about 400 kilometers per second. Now, as a speed, that's not really surprising, because they already knew about the solar wind, which is plasma streaming out from the sun all the time. The solar wind really shouldn't be quite that fast close to the sun, and it clearly was a structure, so they were not anticipating that. Jack Eddy, who was interested in history of science, went to look through a stack of solar eclipse drawings of corona. That was something that had been done for quite a long time already at that time. And less than a year from Carrington's flare, there was a drawing that was made in Torreblanca in Spain that looked like this. Now, if you look at it, there seems to be a bright core. Yep, check. There seems to be a cavity. Yep, check. And there seems to be a bright front. Yeah, check. So it looks like if they had known what they were looking, they could have found a reason, an explanation of how something happening in the sun can influence the Earth. Of course, solar eclipses last only a couple of minutes, so most likely they would not have noticed any movement in here. But it's interesting to see that there was actually an observation like this. From the modern times, I found one other solar eclipse in the 2020 mentioned, where there was clearly a solar eclipse, and that was really clear. It was also observed with a coronagraph. Nowadays, we of course observe coronal mass ejections regularly with things like the LASCO on board SOHO. So here, this is the C3, the larger aperture of the LASCO instrument. This circle in here is the sun, so it's blocking quite a lot of the solar radiation. There's also C2 that looks a little bit closer. But you can see the flows from the sun, continuous flows, and then you can see the CMEs. And as you can see, there were quite a lot of CMEs. This is from the May events last year, and the sun is really actively pushing stuff out. We have quite a good idea what the flares are, what the coronal mass ejections are. They have a flux rope structure, and we believe that they are due to filaments that are threaded with this kind of structure. And you can see here, this resembles very much the flare picture that I showed earlier. So there was this region where the field lines touch, and then these would be the shining X-ray and UV arcs. So when there's a reconnection, these flux rope can erupt into the space, and when it goes further into the space, depending on how much energy there is, it can be pushing a shock wave in front of it, and that shock wave then can be observed with in situ instruments. And the flux rope, more crucially, the flux rope has been regularly observed, so we know that there is this kind of helical structure within the coronal mass ejection. The flares, CMEs are typically related to flares, but not always. There are some stealth CMEs that we can see that we can't see any kind of flares. Also, the flare intensity does not go hand in hand with the CME speed. Statistically, yeah, they go the same way, but not in a way that we could say that, okay, we have X something class, so the CME will be that speed. So it is very difficult to predict the CME from just looking at the flare. Okay. Okay, so the CME is going out, and in some cases it will reach Earth. So in this very nice animation, I'm showing what happens when a CME hits the Earth's magnetic field. So you can see the Earth in there, you can see the Earth's magnetic field. It's not the dipole that you remember from, say, nice dipole field drawings or file and the bar magnet experiments. It's squashed on the day side, so the sun is in that side, and then it's extended into a very long magnetotail. That's because of the interaction with the solar wind, which is blowing all the way, all the time from the right, and the magnetosphere, which drives currents, and then these currents change the shape of the magnetosphere. So if we click and we get this very nice animation of a CME, we can see a magnetic field line. Magnetic field lines aren't real, so this is just a depiction of what happens. But it's a nice depiction, and what's important is the orientation of the magnetic field. So if the Earth's magnetic field here is pointing up, and if the coronal mass ejection's magnetic field is pointing south, so essentially if it has a significant southward component, we can have a reconnection, which is basically the same process that we had in flares. And what the reconnection does is it peels a layer of the magnetic field. Again, we are talking about magnetic field lines; they don't exist, but it's a useful depiction of how it works, and joins it into the heliotail. So sort of peeling an onion from one side to the other side. What's important is that this causes disturbance in the heliotail. So the heliotail becomes unstable, and it can cause vibration. It can cause these inner parts of the heliotail to start converging and resulting in a new reconnection site. A reconnection again accelerates particles into a field line, but the field line is closed. So the particles can't escape from there. The only way they can get out, so to say, is let's go back in here, is to get into the Earth's atmosphere. and that's where the aurora are born. The stronger the eruption, the bigger the disturbance, the closer it is, and the more south these aurora take place. And the aurora are, of course, nice and interesting, but they also are somewhat troublesome. And all of these things that we are interesting, the solar radio bursts, the flares, can have the potential to disturb humanities and our actions in space and ground quite a lot. The UV from flares can increase the ionization of the ionosphere, which will disrupt radio. We are very happily using the radio on the assumption that the ionosphere is stable. The navigation satellites are very critical on what the ionization state is. If there are some plasma bubbles, if the ionization state changes, then there may be a change in the propagation time of the signal from the satellite to the station, and the timing is really what we need to have exactly right for the sat nav to be give the right position. So if you have a big geomagnetic storm, just look at the GPS in your phone and see how accurate it is and how well it jumps. So we have the radio, mobile satellite communication disturbances. We have electric grid disturbances. We don't have the telegraph wires anymore, but we have very, very long electric grid cables, and they also get induced currents, huge currents, which then can damage the transformers. And if the transformer is out of play, then we don't have power. The power can also be induced in gas and oil pipelines. There it will cause corrosion, which is again something that you wouldn't quite think about. We have energetic particles, which I'm going to talk a little bit in a moment. I'm running out of time. They can damage satellites with just tripping bits from 0 into 1. So computer programs don't like if a bit is flipped. They can also damage the microchips permanently. So that there is a very serious problem for satellite communications from that way as well. And the energy particles are ionizing radiation. So if there is a big solar storm, if there's a big solar flare, then the people on a space station might need to go into a specially sheltered area. Finally, there's atmospheric drag. The effect of the solar eruption can heat the atmosphere, and the atmosphere swells. And low-lying satellites will experience a stronger drag. That's what's happened to NASA Skylab. It wasn't up there as long as they wanted. It came down because the solar activity was quite high, and it just its orbit started degrading. Elon Musk has also lost satellites of the Starlink satellites because of this. I still have the 25. It should be 24, but I think it has been happening statistically for a longer time. What do we need to be able to forecast these space weather events? Well, there's a lot of physics that we know, but there is also a lot that we really would like to see. We are still in trouble of trying to forecast when these eruptions take place. We know that the magnetic complexity of the active region plays a role, and the rate of changes of these complexities, but it's still very difficult to forecast it. What kind of CME do we get before we see it? At the moment, we can't say just from the flare, is it going to be a big kind of fast one or not? Is it coming towards us? Well, if it's like this, we know that it's not coming towards us because it's going that way. But if it's what's called a halo CME, then which has components in all of the sides of the sun, then part of it might be coming towards us, and it might hit us. It might be a weak hit. It might be a very strong hit. When will it hit us? There's a lot of uncertainty in there as well, because we don't quite understand how the drag of the solar wind affects the propagation of the coronal mass ejections. And then finally, which way does the magnetic field point? If it's northward, it won't be as bad as if it's southward. So there's a lot of things that we are still looking into research-wise, and also in the space weather operations-wise to improve. So just a couple of minutes, so I'm running low on time, on energy particles. This is what I'm doing. I started my career on an energy particle group, and I've kind of been stuck in that field ever since. So during solar eruptions, these flare processes, as well as the coronal mass ejections, can accelerate particles into relativistic energies. And these particles can escape into interplanetary medium, and in the interplanetary medium, they typically follow the magnetic field line, and the magnetic field, on average, is in these kinds of spiral shapes. That's because there's a solar wind coming out, and the sun is rotating. So it's kind of like a sprinkler effect if you wave a water hose like this, and you look at what kind of pattern the water is forming. It's forming these kind of Archimedean spirals or Parker spirals, as Eugene Parker predicted them that shape quite some time ago, 70 years ago, I think. Okay, so if the particles were just following the field lines, in this particular event in 2010, the particles would be going into this direction. So the flare longitude is in here, Earth is in here, and a couple of other spacecraft, Stereo A and Stereo B, which were in an interesting orbit. One is going ahead of Earth's orbit, so it's a little bit closer to the sun, and the other one is going a little bit further, so it's going behind. So it's Stereo A and Stereo B, or Stereo ahead and Stereo behind. So we would expect that if the particles were accelerated just at the flare and they would just be following the field lines, we would be seeing particles only in here. But we could see particles everywhere. So we could see particles at stereos, and we could see particles, not that many, but still a single, at Earth when the connection is actually on the opposite side of the sun. And that's something that was not really expected. And we have quite a lot of these kinds of events, solar eruptions, where we have particles observed in all sides of the sun. So there are a couple of possibilities. One possibility is that we have a large source region. If the particles are accelerated by the coronal mass ejection, the coronal mass ejection can be very large. But then there's the question, can it be so large that it goes all around the sun? Then the other option is that this is caused by how the particles are propagating in this heliosphere. We know that the magnetic field is on average the shape of the Parker spiral, but we know also that the solar wind is a very turbulent place. It's plasma turbulence, which means that also the magnetic field is kind of random. And that magnetic field randomness makes the magnetic field lines themselves random walk. So if we have particles starting at a given location, a very narrow location, then the particles can start spreading around the nominal Parker field, which is not drawn in here, and follow these random walking meandering field lines, and eventually spread into a much wider range of heliosphere. So that's something that we've been doing with a couple of models, trying to understand how the particles could spread into wide ranges, how that depends on the properties of the turbulence, and could this be an explanation for the wide SCP events? It's an ongoing study, and it's quite an interesting study. It has an importance for the forecasting of the SCPs, but it's also interesting, which is why we do things. Okay, so a couple of new missions, which actually are not that new anymore. I kind of forget how time runs. In 7 years ago, we had 2 new satellites launched, well, spacecraft rather than satellites. The Parker Solar Probe, named after Eugene Parker, which was launched in 2018, and the Solar Orbiter, which is an ESA mission. And both of these missions were going closer to the Sun. Before this, the closest approach to the Sun was at 0.3 AU, but there were no imaging instruments. And that was the Helios missions in the 70s. Parker Solar Probe is went really close to the star, so it goes to 0.04 AU from the Sun, so only 9 solar radii. It's in a very elliptic orbit, which means that it really whizzes by when it's at its closest point. And there's a very good reason for it, because it's very hot there. There are no sun-looking telescopes in that spacecraft, because they would cause the spacecraft to burn. It's mainly in situ instruments, which means that they are measuring the solar wind, plasma, and particles where the spacecraft is. So they are observing the solar energy particles, they are observing the solar wind densities and the electric and magnetic fields and radio, trying to understand solar wind and also some of the solar energy particle and turbulence physics. There is one telescope. It's a telescope that is not looking at the Sun. It's looking decidedly away from the Sun, sideways to the Sun, and observing that. It's kind of like a coronagraph, but it's just not centered around the Sun. It's just looking at one side. The Solar Orbiter has a full set of imaging instruments. It doesn't go that close. And it also has the particle instruments. Its specialty is that it is going to higher inclination. And that's very important, because until now, we have had no idea what exactly is at the solar poles. There's been one spacecraft called Ulysses that went all around the solar poles, but again, no imaging instrument. Its perihelion was at 1.5 AU, and aphelion somewhere around Jupiter's orbit. So for the first time, right about now, we are seeing the solar poles, and that will be interesting for the understanding of how the solar magnetics work. These spacecraft aren't just 2 individuals. There's a lot of work done in comparison. When Parker Solar Probe goes to close to the Sun, it might be measuring the solar wind that is going to to Solar Orbiter as well. So there's a lot of joint science that is being doing with us. And at the moment, we are really in a nice situation that we have a lot of spacecraft that we can use. We have, of course, by the Earth, we have the SOHO, we have the WIND spacecraft with the radio instrument that I mentioned. We have ACE, which is a particle mission. We have the GOES, and just last week there was a launch of IMAP mission. And together, it was a launch with 3 different spacecraft, and one of them was strangely named the follow-on mission, which is a space weather mission with a coronagraph. And that's very important, because the coronagraph on SOHO, which we are really relying on, is almost 30 years old. If it breaks, we are in trouble. But now we have a new one on the follow-on. Then we have the Parker Solar Probe, and we have the Solar Orbiter. They, of course, orbit the Sun. And we also have some support particularly for energy particles, from Bepi Colombo, which is a Mercury mission, and from MAVEN, that is a Mars mission. So whenever there's a solar eruption, we can use all of these spacecraft to find out what is going on and improve our knowledge about these eruptions. I should say that we only see stereo A in here. Stereo B is probably somewhere around here. Unfortunately, we lost connection to it in 2014 when both spacecraft were behind the Earth. So stereo is kind of a mono now. Okay, so I'm finishing up with the summary. Sun is an active star and it has variation timescales from centuries to years to minutes to seconds. And we are observing it with a wide range of electromagnetic spectrum, as well as particle radiation to tell us about different phases of solar eruptions. These eruptions can be very disruptive for our environment and technology, which is why space weather forecast is actually a very active region on governmental and intergovernmental level. The forecasting of energy particles, what we are doing is complicated because the particles travel through turbulent fields. But yeah, that's for me, that's a interesting scientific endeavor. Thank you.
Okay, Timo, thank you very much. It must have been an interesting talk because there is a long string of questions in the chat. And that's before we actually invite people to fire questions at you. So I'll try and sort of break them up and summarize. It starts off, there are a couple of questions about the polarity of the magnetic field for incoming solar wind and CMEs, and why you mentioned it, if it was south facing, why that was more energetic or disruptive.
It's got to do with the magnetic reconnection, which is kind of a tricky topic. But if you can see my camera, if you have a magnetic field going in that direction on this side and that direction on this side, and then you're pushing them together, you get an area where the magnetic field goes to zero. And that's important because when you have a strong magnetic field in plasma, the plasma is confined to move with the magnetic field. So we're talking about frozen in condition. So if the magnetic field moves, then the plasma moves with it. If these magnetic fields like this get close together, the magnetic field goes to zero, and it enables this frozen in condition to break. And that makes it possible for the magnetic fields to reconnect in here, and instead of being connected up there, being connected in here. Now that doesn't work if the magnetic fields are in same direction. If they're in same direction and they push them together, the magnetic field is actually getting stronger. So that's why you have to have the opposite polarities.
And I think the question is also referring to that mechanism is what makes the effect on the Earth and aurora more dramatic.
Yeah, it's kind of, you could say that nothing happens if the magnetic field is north, but that's not true. There are some mechanisms that will work in that case as well. But it's definitely stronger if you have this reconnection in here. I think there's some speculation that if it was a north field, then the reconnection would not happen here, but it might happen somewhere in here, where the polarities again you would have the this kind of feature in there.
Okay, the next question from Martin Kinder. Coronal holes affect solar wind and hence the magnetosphere. Why do they cause auroral conditions? And allied to that, how is the magnetic polarization of CME determined in advance? Now, Martin's then typed answered after that. So I'm going to assume he'll sing out if it's not answered. But I think there's an interesting question I'd like to ask is, how do you determine the magnetic orientation of a CME as it's approaching?
You can't. That's the problem. That's really the it would be a very big step forward if you could figure out what the orientation is beforehand. There is a mission called Hinon that is going to be launched. I can't remember when, where the do I have a suitable picture? Hold on. Okay, this isn't the perfect picture, but it's essentially a spacecraft that will go on orbit like this. So it will get, I think, as far as I remember, it's a constellation of several spacecraft. And the idea is that one of the spacecraft is always closer to the sun, somewhere not too far from Earth, but still closer than the L1 point, Lagrange 1 point that we now have. And that can then measure so you can measure the magnetic field by magnetometer in the spacecraft. So the idea is that if we go closer to the space between the sun and Earth, then you can measure it, and then you have your information.
Okay, Lynn Smith asks, if the intensity of a solar flare doesn't trigger a CME, do we know what mechanism does?
It's always some kind of instability. It could be that it's something that isn't overly energetic. I'm not sure what that mechanism would be, to be honest. There just are these reports of coronal mass ejections where you don't have a flare.
Okay, there's a couple of questions about the probe itself. Extreme events and their effects on those two solar probes, the Parker and the Solar Orbiter. Presumably they get fried.
At some point, yes. They do have the same problems. They do have electronics that can get hit by particles. They tend to be very radiation hardened, so you can get radiation hardened components, and there can also be quite a lot of redundancy. So I kind of remember that there's kind of, I think in Soho, you would have checksums calculated of the code, of the machine code, checking that it hasn't changed. So, and then the code, if it has to reboot, it's loading the code from a very radiation hardened source. But that said, at some point, something may happen that fails. And Yoko satellites that I showed in is it here? As far as I remember, it was lost because of something, and we don't really. I don't think we really know what happened. But if you lose a communication to a satellite, then it is very difficult to return to it.
Okay, there's two last questions, and I'll throw it open to people just to fire questions. One is, have Carrington events been seen around other G-type stars? And if so, is there any record of that showing up in Earth's geology? And the last one is, will SWFOL1 improve solar weather prediction? I presume that is a satellite mission.
Yeah, that's, if I answer the latter first, it will, I think instrument-wise, it's not going to bring anything new, but it's going to bring, well, it's going to bring a very important replacement and redundancy for LASCO, because it really is an old instrument. And it's having redundancy, having that assuredness that, okay, if something breaks, then we have at least something else that can do these observations. So that's really the big importance. As far as I recall, it is an operational satellite. So it's not a science satellite. It's really there to do observations for space weather forecasting. The first one, flares are seen on other stars. There have been quite a few sessions in meetings kind of having people from stellar communities and from solar communities doing comparisons. I haven't really followed that closely. There's also coronal mass ejections have been seen in some stars as well. So again, I'm not an expert on that field, but as far as I understand, they have to be quite substantial in comparison to the solar ones that we can actually see them.
That is an impressive observation, I have to say, and something I couldn't have imagined happening and seeing the results of that. Right. Any questions? If you have questions, please just unmute yourself and fire your question.
Yes, just say thank you for the
Thank you. Thank you.
Any more questions?
Do we have any understanding what caused the Myaki events at all?
I think it's difficult to say what caused them. I think there has been some speculation. I just recently read an article about them. Yeah, I don't know. I mean, there are events, particularly on the sort of longer time scales that indicate that there have been these very massive solar eruptions. We don't know what causes the really massive ones. We don't know if the physics is the same or not, if it's just potluck. At the moment, it's mainly kind of an extreme event statistics that has been thought that, okay, at some point, the odds will be such that something really big will happen. But yeah, I don't know.
Diane.
Timo, thank you. Very interesting presentation. You were saying about the effect on the atmosphere due to magnetic interference causing aurora. Do we know if when the solar wind departs from the sun, the magnetic orientation is the same, or does it rotate?
There have been some theoretical work on erosion or accumulation of coronal mass ejections as they come through. There may be some reconnection, so we don't know if it's exactly the same. That's a very good point. One thing that I could also add is that something that we know that has influenced at least some big geomagnetic storms is that if you have plenty of CMEs, and there's a latter CME is faster than the first CME, they can interact, and the latter CME can enhance the magnetic field of the first one. So there is a thought that these interacting CMEs might be causing bigger geomagnetic storms. It's not certain because the statistics aren't huge. But for the May event last year, I think there were something like 7 coronal mass ejections between Sun and Earth at the same time. So it makes studying these things very difficult, I would say.
Yes. And again, thank you. Very good presentation.
Thank you.
Any more questions? No.
I think there's someone in the chat. Okay, there was a thanks in the chat. I'm not quite sure if there was one question that you asked from the. No. I misunderstood that you read a question, and I wasn't sure if I answered it.
Unless you want to talk about interdigital filters.
Oof, no.
Okay, if there are no more questions, I think it's to thank our speaker for a very interesting and lucid presentation. I for one thoroughly enjoyed it. And a few notes. Our next presentation is Friday, the 7th of November. which will be on ultra-high energy cosmic rays and neutrinos and detecting them through their radio signal. And that, again, promises to be a very interesting presentation because it takes us back to some of the foundation work of Jodrell Bank and Francis Graham Smith, who died in the summer. And that's a nice connection back into our own history. And then Friday, the 5th of December, Diane Swan will be talking about core collapse, supernova, and the radio signals of supernova 2017 EAW, and a few words about the E Merlin array. So that's something to look forward to between now and Christmas. So once again, Timo, thank you very much for your time, and thank you very much for a very interesting presentation.
Thank you.
I'm now going to